Okie dokie. Lesson 95. Since I didn't receive any questions on lessons 92, 93, 94, I can only assume that everything went swimmingly. So lesson 95 is about finding the volume of what are called right solids. Now, a right solid is just a shape, a three-dimensional shape, where the angles are right angles like that. So we have a right angle there. We have a right angle right there. From the base going straight up, there's a right angle. There's a right angle between there and there. And there's a right angle from this base here to there, you know. From that. So as opposed to, say, like a pyramid, definitely not right angles there, or a cone, okay? Now, another word a lot of books would use for these are called prisms. So this would be called a triangular prism. Triangular prism, that's a cylinder, of course, cylinders. This would just be some sort of rectangular type of prism. It's not a fully rectangular prism. A box would be a rectangular prism. But they're all right solids because once you conclude the base, if I were to set this up on its end, or that up there, it goes straight up. It doesn't slope or anything. So there we go. That's what our right solid is. So to find the volume of a right solid, the formula is pretty straightforward. You just find the area of the base and then you multiply that by the height. And that will give you the volume. Now, all of these dimensions are in centimeters, so it's going to be important for us to include that in our final answer. Since we're multiplying, we're multiplying three things that all have centimeters in them. My units for volume will be centimeters to the third power, or centimeters cubed. All right, so let's look at this first example right here. So this is a right solid, a triangular prism. And this portion here, that's our base. So everything takes off at right angles from the base, going up that direction. So to find the volume of this, I need to find the area of the base. Well, that's just the area of this triangle, and multiply it by the height, which is 12. So you recall the area of a formula for the area of a triangle is 1/2 the base, which is 6, times the height, which is 8. So that's the area of the base. Now, a lot of books will use a capital B to represent the area of the base, as opposed to just a lowercase b that just represents, say, the length of a side. But at any rate, this is the area of the triangle, so I'll take the area of the base and I will multiply that by the height, which is 12. All right, well, 6 and 8 is 48, and half of that is 24. So 24 times 12, well, that's 12 times 12 times 2. You can look at it that way, but at any rate, it's 288. And since, again, this is measured in centimeters, this is measured in centimeters, and this is measured in centimeters, my final answer takes centimeters times centimeters times centimeters, or centimeters cubed. So there's our answer for part A right there. The volume of that right solid is 288 cubic centimeters. All right, we have a similar thing going on here. It's just a triangular prism. We'll treat this portion here as the base and goes up that direction. So we just need to find the area of the triangle there. So again, we'll use the area for the formula for the area of a triangle. So that's 1/2 times 10 times 6, and then times the height, which is 12. Now, 1/2 times 10 times 6 is 60, so half of that is 30, and 30 times 12 is 360. 360 what? Well, centimeters times centimeters, again, centimeters cubed. As we've discussed in class, area is measured in square units, volume is measured in cubic units. All right, so now we have a cylinder. And you're saying, gee, that doesn't look like these. It doesn't matter. All that matters is that the bottom or the top is at a right angle to the sides. That's what makes it a right solid. So the formula still holds. It's the area of the base times the height. The only difference here now is that our base is a circle. So I just need to find the area of the circle and multiply it by the height, which is 10. Well, we have a circle here whose diameter is 6. You will recall, I'm sure, that the formula for the area of a circle is pi r squared. That's the area of a circle. Good. So here, if the diameter is 6, that means the radius is 3. So r is 3. So to find the area, the volume of this, we'll start with the area of the base, which should be pi times r squared. So that's the area of our base. I just need to multiply that by the height. So multiply this by 10. And it says to leave pi as pi. That means I'll just write pi times 3 squared. It's just 3 squared is 9. So this will be 9 pi times 10. And 9 pi times 10 is 90 pi. And again, that is cubic centimeters. 90 pi cubic centimeters. There we go. Let's underline those answers there. All right. There you go. See, it's pretty straightforward stuff. All right. Let's look at D here. Now here, our base is kind of L-shaped, isn't it? Yeah, this will be our base right here, and our height is just 10. So I need to find the area of this base. Well, we don't have a formula for the area of an L shape, but if we just break it up into two things that we do have formulas for, namely two rectangles, and if you consider what's going on the other end there, this is 3. That means this rectangle here is a 5 by 3. And this rectangle right here, well, if this is 7 and that's 3, that means this distance here must be 4. And we know the height there is 2. So this is a rectangle that's a 2 by 4. So we're going to take the 3 times the 5. That will give me the area of this rectangle. And we're going to add to that 2 times 4. That will give me the area of this rectangle. And adding those two together gives me the area of the entire base. That plus that. And then we'll multiply that by 10 to come up with our final volume. So here's the area of the base by splitting that into two rectangles and multiply that by the height. Bada boom, bada bing, we're done. So what is this problem here? 3 times 5 is 15, plus 2 times 4, which is 8, times 10. Well, 15 plus 8 is 23, times 10. Well, that's 230 cubic centimeters. Don't forget your units. And finally, this E here, again, this is just a cylinder laying on its side, doesn't change anything. In this case, we have the base, which is a circle, and the height, which is 10. But here, they give us the radius, and the radius there is 1. So R equals 1. So that means that the volume should be the area of the base. Well, the area of a circle with radius 1 is pi times 1 squared. And then I'll multiply that by the height, which is 10. Well, pi times 1 squared, it tells us to leave pi as pi. 1 squared is 1, so 1 times pi is just pi. And pi times 10 then just becomes 10 pi. And there you go. A, B, C, D. So the formula for the volume of a right solid is just the area of the base times the height. It's that straightforward. There you go. Very good. All right. Let's look at problem set 96. Now, 96 is one of those lessons where they combine two things which have almost nothing in common. They're combining angle measures, and then they're combining that with distributive property, which is these down here. So let's look at angle measures first by looking at the practice problems here. Now, they're using the minute hand on a clock as it goes around to illustrate how you can visualize angle measures without, saying, having a protractor right at hand. And the idea is fairly straightforward. There's 60 minutes in a whole rotation of the clock. So I mean, this, 5, 10, 60 minutes in a whole rotation, which the minute hand does in 1 hour. And it's covering the entire circle. Well, we all know that the distance in degrees for an entire circle is 360 degrees. And if the minute hand passes 360 degrees and there are 60 little increments there, each representing a minute, then that means each little minute increment is 360 degrees divided by 60, or 6 degrees. So that means a distance of 5 minutes on a clock face means the clock has to go through 5 times 6, or 30 degrees. A distance of 15 minutes on the clock, well, that's 15 times 6, which is 90. So that would cover a distance of 90 degrees. So that's how they're going to use the clock face here. And so by calculating minute marks, we want to find the measure of each angle shown on the clock face. So let's start with AOB. If you look at that carefully, you can see that that covers a distance of 1, 2, 3, 4 minutes. Since each minute represents 6 degrees, AOB should be 6 times 24, should be 6 times 4, which is 24 degrees. There you go. There you go. AOC, so again, starting at noon, we're going to go all the way down here to 4, which is 20 minutes, and each minute is worth 6 degrees. So 20 minutes times 6, that is 120 degrees. There you go. And finally, AOD. Well, starting from the 12 here, and we count back to the where our D line is, and that's 1, 2, 3, 4, 5, 6, 7. So there's 7 minutes between those two. Each minute is 6 degrees. It sure looks to me like that's going to be 7 times 6, which is 42 degrees. So there you go. I'm just estimating those measures based on the minutes on a clock. Each minute were 6 degrees. All right. Now, in conjunction with that, we have these problems here. We want to estimate the measure of each angle. Then we'll use a protractor and measure each angle and see how close we get. All right. So we can work at this a couple ways. Okay. Let's label this a bit here. So this will be our 12 o'clock. This will be our 3 o'clock. That'll be our 9 o'clock. Okay. And we could try and guess what those minutes are, but let's look at it this way. Okay. So let's start with this E angle. What is this angle right here? Well, we know that where the 12 o'clock comes down to meet the 9 and the 3 o'clock line, that's 90 degrees. And this to me looks like it's halfway between the 12 o'clock and the 9 o'clock line. That's 90 degrees. That means this angle here, I'm guessing, looks to be about 45 degrees. I think that's reasonable. Sure. Now, if I look at this angle here, boy, that looks like, again, this whole distance from 12 down to 3, that's 90 degrees. And that looks to be about a third of that. Yeah, looks to be about a third of that. So the third of 90, I'm going to guess that this angle here is going to be 30 degrees. Yeah. And which would mean this angle right here would have to be 60 degrees. Now, that means this angle here is also 45 degrees. So this large angle here is 45 degrees. So from there to there, if that's 45, this must also be 45. Now, if I look at this angle here, that thin angle right there, it looks to me like that's a third of this angle. So I'm going to guess that this angle right here is 15 degrees, and this angle right here then would have to be 30 degrees. So now we've pretty much labeled everything. Let's find the measure of angle BOC. So starting at B, I'll go B to O to C, from there to there. And by my estimation, I'm guessing that is going to be 60 degrees. All right, so far so good. E says DOC, so I'll start at D, I'll go down to O, and then back up to C. That's that little sliver of an angle right there, which by my estimation is 15 degrees. All right. Now FOE, let's start at F, let's go to O and out to E. Clearly that looks to me like that's gonna be 45 degrees. And finally FOB, oh my word, that goes FOB, that's that big angle right there. Well, I know from there to there is 90, and from there to there is 60, so I'm going to say that should be, by my estimation, 150 degrees. All right, now let's see how close we are. I actually have a, oh dear, actually have a protractor. I printed out, and you can just download all sorts of images of protractors online if you don't have your own protractor. So you need to line that up with my 0. So my 0 here is going to go right at the 3 and over 180, over at the 9. Make sure that's pointing right up there at the 12. All right, so let's see how we did here. BOC, I guess was 60 degrees. Well, let's see what it really was. This is going from 90 down here to B, which goes right out to there. And that sure looks like that's going to be, whoops, hang on, get my pen to work there. That looks like that's 36 inches. I called this 30. That means this distance here is going to be 64 inches. No, it is not going to be 64. It's going to be 54 inches. 54 degrees. So yeah, so what this, I thought it was 60, I eyeballed it, but my protractor tells me it's really 54. So let's cancel that out and write 54. So 6 degrees off, which would be 1 minute if we're going by the clock there. All right, let's look at FOE. F, you recall, is right there. So I'm going to start down here. So F, O, and out to E. And sure enough, that's going to cross right there at 135. That means this angle is indeed 45 degrees. Yay! Let's look at DOC. Well, look at there. That goes from 90 out to 105 right there, which is 15 degrees. Excellent. Now, we already know that this one I got wrong. I thought it was 60. But it's 54. So that means that this angle, FOB, will be 90 plus 54, which is, of course, 144 degrees, not the 150 that I estimated. There we go. All right, good. So just need to use some eyeballing, some estimating, and then get out your protractor and see how well you did. All right, so the second part of lesson 96 is the distributive property. And the distributive property simply says that if I have something that's multiplied by an expression in parentheses, that when I get rid of the parentheses, I have to multiply this value that's outside the parentheses by everything inside the parentheses. So that means I'll have to take this x and multiply it by x, and then take this x and multiply it by minus y. That's called distributing the x. So for h here, this is simply going to be equal to x times x, which is x squared, minus x times y, which is x, y. There you go. You just simplified that. Boom. All right, so let's look at I over here. Same way. I've got a minus 3 times the quantity 2x minus 1. So when I distribute that, I'll take minus 3 times 2x. That will be a minus 6x. And I'll take a minus 3 times minus 1, which is a plus 3. So that simplified is minus 6x plus 3. J says minus x times the quantity x minus 2. So minus x times x is equal to a negative x squared. And minus x times a minus 2 is equal to a positive 2x. So x squared minus x squared plus 2x, because minus and minus is plus. All right, K. Minus 2 times 4 is going to be a negative 8. And minus 2 times a minus 3 is a positive 6x. So that simplified is minus 8 plus 6x. All right, let's simplify this right here. So we have x squared, nothing to do with that, plus 2x. Now, we distribute the minus 3, so minus 3 times x is minus 3x, and minus 3 times 2 is a negative 6. Now, these two x terms that both have an x in them, they're what we call like terms. I can combine those. So my final answer will be x squared. Well, 2x minus 3x is a negative 1x, or negative x, and minus 6. So that simplified is x squared minus x minus 6. All right. Over here we have a similar type of situation. We have x squared, nothing to do with that. We've got 2x. Now we distribute the minus 3. That becomes a minus 3x. Minus 3 times minus 2 is a positive 6. There we go. Now again, I have a 2x and a 3x. Since they both have an x term, I can combine them. So this is going to be x squared minus 2x minus 3x is a minus 5x plus 6. And there you go. Done. So that's just distributing. Pretty straightforward there. All right. And finally, lesson 97. Pay no attention to that noise. Here you are asked to consider two triangles that, although not exactly the same size, are what we call similar triangles. Similar triangles are triangles where the angle measures are the same. And since the angle measures are the same, the lengths of their sides correspond to one another. It may be one's twice as large as the other one, but the angle measures are still the same. So if the angle measures are the same, then we say that those two triangles are similar. Similar. And to represent similar, as opposed to equal or congruent, we just use a little squiggly like that. So you can see that these three tick marks mean that W and R are the same angle, Y and Q are the same angle, and X and P are the same angle. This triangle is smaller than this one, but since the angles are all the same, these are similar. There's some correlation between WY and RQ, WX and RP, YX and QP. So to write down the similarity, we just have to make sure that when we write this triangle down and we make this one similar to it, that the letters in the triangles match up with its similar components. In other words, I'm going to call this triangle right here WXY. Now I could call it YWX or XYW, but I'll go in alphabetical order, call it WXY. So this says triangle WXY is similar to. Now this triangle likewise I could call RPQ, PQR, or QRP. But to show the similarity, I want to make sure that I orient this triangle in the same orientation as this one. So triangle WXY is similar to triangle? Well, W corresponds to R. There we go. R. X corresponds to P. And Y corresponds to Q. So once you settle on naming one of your similar triangles, you just have to make sure this other similar one that you're naming, the vertices match up. W is to R, as P is to X, and Q. Whoops, I wrote this wrong. That's not a Y, that's a Q. There we go. Q is to Y. That's called a similarity statement. There you go. All right. Now, if we look at these two triangles here, again, since these two angles are the same, then that third angle has to be the same, doesn't it? Because we know that all the angles in a triangle are equal 180. And since these two angles are the same, whatever the measure of this angle is, it has to be the same. Otherwise, these wouldn't both equal 180. So that tells us that these two triangles are similar. All right? And just to reference them, I'll tell you what I'm going to do. I'm going to call this one A, B, C, and this one D, E, F. So if I write a similarity statement here, I would say triangle A, B, C is similar to triangle D, E, F. Because A corresponds to D, B corresponds to E, and C corresponds to F. So there's my similarity statement. Now it also says something about the length of the sides. So what we can say for instance, the side AC here corresponds to the side DF. That means if we compare these, we can say that 6 is corresponding to 9 in this example. We can say that X is corresponding to this side, so the length of this, which is X, we can say that X is corresponding to 12. And we could say here that 12 is corresponding to Y. Now, those comparisons hold true. So as long as I'm making sure I'm going in the same direction each time. So here I'm going always from triangle ABC to triangle DEF. I'm always going from the smaller one to the larger one. Smaller to larger, smaller to larger, smaller to larger. So we can use these relations to say find the information we want. So let's find the length of side X. All right. Well, according to this, we should be able to say that 6 compares to 9. So I'm going to say 6 is to 9 and set up an equality that says as X is to 12. X is to 12. So I just set up a ratio there. 6 is to 9 as X is to 12. We can do that because and only because these triangles are similar. If the triangles weren't similar, these ratios wouldn't hold. But because they're similar, whatever the difference is between one, like say this side AC and this side DF, that difference is going to hold for all the sides and all the comparisons. So 6 is to 9 as X is to 12. So how do we solve something that looks like this? Well, we cross multiply, right? So this says 9 times X is equal to 6 times 12, which is 72. And that means that X is equal to, divide by 9, 72 over 9, which is, of course, 8. So X right here equals 8. There we go. Beautiful, beautiful. Find the length of side Y. Okay. Well, we can do the same thing. So we can say, well, I'll just use 6 to 9 again. I'll say 6 is to 9. Now we could use, now that we know that this is 8, I could also use 8 is to 12. That's fine. Again, the ratios are the same. It doesn't matter which side you use as long as you keep them corresponding. This side is to its component side. So 6 is to 9 as 12 is to Y. So 12 is to Y. All right, so let's do the math here. We're going to cross multiply 6 times Y equals 9 times 12. Well, 9 times 12 is what? Well, I believe that is 108. There we go. So, to solve this, I need to divide by 6. So y equals 108 divided by 6. And you guys know how to do that in your head. 6 goes into 10 one time with a remainder of 4. 6 goes into 48 8 times. So y here equals 18. And all those numbers make sense. We know that x should be smaller than 12 and 12 should be smaller than whatever y is, and that all fits. So once we know that two triangles are similar, and we know that if we can show that the angle measures are the same, then we can set up these ratios and decide all sorts of things about those triangles. Okay? Let's look at an example of this where we have a tree that casts a shadow 18 feet long while a 6-foot pole casts a shadow 9 feet long. How tall is the tree? Well, I'll tell you what, let me move this up a bit and get another piece of paper here. So I can draw a nice little picture of that setup there. There we go, right there. That'll be just fine. So you have a tree casts a shadow. So let's start by drawing something that will give us a shadow. Let's draw the sun. The sun's this big fiery ball up there. It's shining down. Here's the ground. And we have a tree. Let's draw a tree here. What kind of tree? I think I'll make it an evergreen. So it'll look like this. And it casts a shadow, so the shadow of that tree, way out here on the ground, that casts a shadow 18 feet long. Wow, okay. So, what else we got? Over here, we have a 6-foot pole. So here's a 6-foot pole somebody stuck in the ground. That's 6 feet. And it casts a shadow 9 feet long. 9 feet long. Well, you know what we can do? Because they're both coming from the same angle of the sun, okay? That means I can, if I want, I can form a triangle out of this. And I can form a triangle out of this. And those triangles should be similar because the angle of the sun doesn't change. So that means these angles with relation to the ground are the same. The pole is sticking straight up, as is the tree. That means these are 90 degrees here and here. And so this is just, there you go. You got your, so those two triangles are similar. And they're asking us to find the height of the tree. So we're going to find the height of the tree, H, right there. Well, the tree represents this side of the triangle, doesn't it? And since they're similar, that means I can set up a ratio. I can say that 6 is to H. So 6 is to H. Again, I went from this direction to this triangle, this triangle, going this direction. So I got to make sure I maintain the direction. So 6 is to H as 9 is to 18. 9 is to 18. There we go. Now I just have to solve for H. So before we do that, please note that we can simplify 9 over 18, can't we? They're both divisible by 9. So this is saying 6 is to H as 1 is to 2. Okie dokie. So now we'll say, well, cross multiply. 6 times 2, H times 1 is H. And 6 times 2 is 12. So that means the height of the tree is 12 feet. And that makes perfect sense if you think about it, because after you see the image, you can see that this side, the shadow of the tree, is exactly twice the shadow of the pole. that means the side of the tree that corresponds to the pole should be twice the length of the pole. Yeah. Yeah. You could determine that length there. That's in the next lesson, I believe, but that's not for us today. We just wanted to find that height, and we did it using similar triangles and ratios. All right, splendid. If you have any questions, you know how to get a hold of me. Great. I'll talk to you later.